Okay, good. So the goal here is try to think about the best approach that we could achieve. So as I said during the talk, the initial approach will rely on having a virtual NVMe controller in PCIe that we could directly attach to the guests. But obviously, ideally, we'd like to have something to be able to directly ask the card to maybe in live to create a volume or a virtual NIC or the kind of thing. So the first question is, I mean, not now, obviously, but in the near future, depending on the feature available on the card, what could we call to that card to be able to do what we need from the DOM0 perspective?
So, I mean, would it make sense to do something like, implement a VirtIO driver? I mean, is that possible? Is that the most wise thing to do, or?
Well, go ahead, Jean-François, to explain a bit how you imagine on your side so we could confront ideas and try to see.
Okay, so just 1 minute. My colleague, my expert colleague is trying to get connected. Let me just write to him.
So, George, the initial discussion I had was maybe having the current Xen PV protocol to talk with the card, but as we found that wouldn't be possible while using Xen because of shared memory access that not possible with the way that Xen is working. So that's why we think that the VirtIO way might be the best one, but obviously depends also on what's inside the DPU and what's exposed and how to contact it, how it's meant to be contacted from the outside. This is something where you, Jean-François, and your colleague might be able to answer.
So what I'm sharing here, and I'm sorry, I'm not familiar yet with Xen, and we're going to do that with Olivier moving forward. I want to share some slides. I'm pretty sure, guys, you'll make the connection. This is using KVM because we had that request from a project. And there are two things. First, the OS, second, the card, the DPU. What is important to understand is from a PCI resource perspective, what we are using as a feature, there are two main features to be used, right? The first one is NVMe emulation. This is standard NVMe feature. What is that? NVMe emulation, first, I forgot to mention, that's important. On the PCI, the x86 is the master controller, is the root complex of the PCI bus. It controls all the resources. So we need to do something in order to have the card controlling the disk drives. So the presentation here is not about smart NIC. It's about really offloading the storage resources, which is really our first aim as a company. So first feature is in NVMe emulation. The card is in endpoint in terms of on the PCI. That's very interesting because when you are an endpoint, then you can publish on the PCI features and up to 256 functions. One of those functions is NVMe emulation. NVMe emulation is very interesting because it makes believe that the card is an NVMe device. So from a host perspective, it's as if you have an NVMe SSD or an NVMe resource whatsoever. So you just need an NVMe driver. So that's very interesting. You don't need a specific driver. That's the first point. Because you are endpoint and you have up to 256 features, you can propose on the PCI bus up to 256 NVMe emulated devices. So for instance, if the card create 256 volumes, logical volumes, your OS will see 256 NVMe drives. So very easily you can mount from VMs, from the hypervisors, wherever you want. you can mount that resource and use it. Now, the other critical point is allowing to connect the devices, the NVMe SSDs, with a card, knowing that you have the x86 in the middle. You may have heard of some great technology advertised by NVIDIA, which is GPU Direct. GPU Direct is using that same PCI feature named peer-to-peer. It's really one way to have a shared memory and to connect two devices to exchange data. So GPU Direct allows to connect an NVMe, a PCI HBA or NIC or drive with a GPU to go fast, because the bottleneck is x86. And this is exactly the same here. We want to bypass the x86. We don't want to have the x86 in the data path at all. So peer-to-peer will allow that connection between any NVMe SSD and the card itself. That way, the card will control the drives as if they are internal drive, right? Then what we do is we are virtualizing those drives. So we are grouping them into a RAID. So RAID means that we provide security, right? RAID 1, RAID 6, whatsoever. It's a matter of price, but it's going to be secured. So the OS will not see the drive anymore. However, we're going to carve that RAID into logical volumes and propose them over the PCI using the NVMe emulation. So from an OS perspective, in Xen, the important part here is how you handle devices, how you control the IOMMU, so that we allow the card to connect with an NVMe SSD. For the KVM example here, we just have a little script that is just controlling the device allocation. That's not very complex, but this is really the connection between the OS and the card. Any question? Oh, okay. Let me continue. So now this is a hardware, and we're gonna test that with Olivier. Normally, you just plug in the card, and it's seen as an NVMe device. Now there's a full layer on the top of it, running on the DPU. Let me give you a rough example of the things we have been running. For us, Olivier introduced it. It's important to be able to manage a lot of number of IOPS and to have resources to offload services. So in our example, we have 80 cores, and those cores are grouped in 5 entities we name cluster. And we have 1 cluster dedicated to control plane and 4 clusters dedicated to data plane, 64 cores. The control plane is important. We have an embedded Linux running, and that Linux is taking control of the drives. This is where you see the direct connection to the NVMe SSDs. We can do the same with HDDs as well, right? It's not a standard Linux, but it's a good enough Linux. And we have the SAS driver. So if your host has SAS SSDs or SAS HDDs, it's going to work as well. So we enumerate the drive. We create the control queues so that we can exchange data with the data plane, right? And this is where we have the management stack as well, to the outside if we need to do external management. I'm not going, you're going to have the slide, right? Not a big deal here. I'm going to go through to the end of the stack so we have a look of what we are doing. So, what we are doing is we want to be as open as possible. We are using SPDK. SPDK, if you don't know that, SPDK stands for Storage Performance Development Kit. You have the same for network, which is DPDK, right? But for storage here, which is the aim of that architecture, is to handle storage. So you have the control part of SPDK, which is controlling, providing an SPDK API to the outside, in-band outside. And you have the SPDK data plane. This is really the BDEV, which are the block devices where you're going to find all the features. So you have standard features provided by the SPDK from the community on GitHub, and we are developing others to complement what is missing, right? But it's really straightforward to have that. This is exactly the same SPDK which is running on an x86. What we have done here, and if you just remember what I've explained a bit before, 5 cluster is equivalent to have 5 CPUs or 5 independent nodes. Here we have created a global SPDK leveraging those 5 entities. So it's from an outside perspective, it's just as if you have one SPDK. We have a complete network stack, because if you do NVMe over Fabric, you need TCP/IP and UDP support, and obviously we have NVMe support to create the link to manage the NVMe commands. Because the beauty of NVMe is NVMe commands are running as well are running on PCI as well on TCP, fiber channel, and RDMA on UDP, right? So it's really the same command set, which is really interesting for us. So on the control plane, we have that NVMe driver to handle the I/O to the drives. So this is the software stack we have. If you want, and this is interesting because and it's more and more widely adopted. If you think about other environments such as OpenStack or Kubernetes, Docker, if you want to connect to OpenStack, you need to develop a Cinder module, right? And today, available is a Cinder based on SPDK. So for us, it's quite rapid, really straightforward we connect our card, and then from a Cinder perspective, you can access command, create volumes, etc. Same in Kubernetes, you have a CSI which is SPDK based, and you can directly get volumes from the card for the application. So that's very interesting to have that perspective, right?
So what you say is basically the API to talk to the card to be able to create volumes, etc., is to go directly through SPDK.
Yes. So I'm just giving you here a yes, but the API today is available from that line here, right?
Okay.
Inbound management. So the thing on the card, we have the 2 times 100 gig to go to the outside, because any volume controlled by the card will go outside and will be accessible by other nodes, which is the beauty out of it, right? We have here a gigabit Ethernet for management, obviously not used here, and you have the PCI. So the work we have to do to integrate a DPU into a virtualized environment such as Xen is to have that SPDK command to be visible from the host perspective. And we need to find a way. This is still the discussion we have to drive, right? But SPDK is really one great way to do it.
Okay, and do you have any already preference or idea on the way that the DOM0 will probably handle that? I mean, how it could talk to the cards from the itself. I mean, without doing an external request through the external network.
No, I don't know yet. Unfortunately, I would have loved my colleague to be online, but he is still struggling. Anyway, we'll try to answer that. But I'm sorry, I don't yet have the answer, and I hope this week we're gonna get that together.
Yeah.
Perhaps the following of the presentation will help you figure out. I'm not an expert in that area. I'm gonna share. My colleague Remy should have done that, but I'm gonna do that for you guys today. And maybe you are familiar with KVM QEMU. And the discussion is about VirtIO and the should I use kernel space, user space, what's the best efficient way to access a DPU, right? So we put those slides together for a customer who's using actually KVM and QEMU to do virtualization, and using a VirtIO driver. There are many ways, right? Either you have the VirtIO driver in the VM and this driver is discussing with a VTIO device directly in the kernel. The problem is this is not really efficient. You're switching from kernel space to user space. This is working, but this is not. You're going to see some numbers. It's not very good in terms of what you can get, right? One good way, obviously, is to have this type of implementation, right? Using VirtuIO in the guest, and having a module directly into the host kernel, not at the QEMU level. Still kernel here, but QEMU directly is not involved into the discussion, so you'll get some gain in terms of handling the IOPS. Still not the best way. Let me jump to what we think is the best way. Here you are, right? For us, the best way, as the card support NVMe, is to talk natively NVMe in the guest OS. That would be a very efficient, because you completely bypass the virtualization. You talk native NVMe, and you no need. You completely offload the virtual host and the storage management from a host perspective.
So the only thing that's needed to achieve that is to tell on boot time the guest kernel at some point where it should talk to exactly. I mean, on which VF it should talk to. But if it's aware about that, that would be it, right?
Yes, that should be it, right? This is our expectation, and this is how it's handled if we use a QVM QM. But I suspect, I suspect you can do the translation with DOM0, right? I suspect it's going to kind of the same.
I think at some point the question is, could we do that? I mean, if we could get at some point when we boot the guests the list of the disks that are related to which VF exactly, and then booting the virtual machine and said that it should use this directly on boot. But obviously, I don't know how that could be done. Maybe George, you have, or Roger, I don't know. Maybe you have some ideas how we could tell the guests on boot to use directly this NVMe drive.
I think it looks like a normal PCI device to me, that thing. So we just assign a PCI device to a guest, and that's it.
So that would be PCI pass-through, right?
Yeah.
Okay, so the question I have is, could we dynamically assign PCI devices to a guest? You know, because on my knowledge right now, when you do on a physical card that you want to PCI pass through to a guest, usually you tell your DOM0 to do not manage this card, to reboot it, and then you can use it from a guest perspective. But could you do that for kind of ranges of PCI addresses on boot?
Yes, I think so. Also, this is an SRIOB, which we already handle for network.
Yeah, it'll make a new one. And you can also, you can unplug something from, I mean, so even if it were already there, you can unplug it from DOM0. So you can tell DOM0, dynamically, stop, stop driving this, and then assign it to the guest, and then, vice versa. So, yeah.
Yeah, because the point is here, what may happen at the beginning is maybe you plug in the card, you get started with DOM0, and you have no devices to show, right? And then you start configuring the card, creating the volumes, so the volumes will appear one after the other, right? The card may control the drives, but may not be configured yet to expose volumes.
Yes, it sounds to be the easiest way to do it. The only thing to make it the flexible way is to be able to dynamically do that from an API perspective, at a higher level, to tell the card at some point, please get me 20 gig of an NVMe drive, give me the address, and then I will pass that to the guests, and I will attach it to the guests, and I will boot the guests. And
Well, I was just saying, from the core, kind of from the XL perspective, that's all kind of storage management. That is not our job. So, like, I think from the if Xen server Rex PNG, we're going to do this. What you want to do is have the storage manager know how to drive this whole thing and get the volumes all set up.
SMAPI v3 should be able to do that because it's completely agnostic on the way it works. So it might be the way to do it. But then the question is, what's happening when you do live migration, for example?
So here, what is interesting, so that card here is controlling the drives from that host, correct? Okay. What is interesting is those drives here, that card is nonetheless doing NVMe emulation, but it's also doing NVMe over Fabric. So every single volume you would have created on that card will be seen over the wire.
Yeah, so it could be a kind of shared storage, and so it means that even if you move the VM, the VM memory to another host in the same cluster, I would say, then you could just say attach on this PCI VF on destination, which is in fact the exact same data than on the source, and then it will make a live migration.
Yeah, there might be some work too. So I think the thing is normally you can't normally if you have something pass through.
Oh, sorry.
Yeah, we lost you, George.
Yes.
But I think this is something that was achieved in Xen server in the past with the vGPU migration at some point. With the NVIDIA GPUs. So
the goal, Olivier, is really to make sure that because when you move a VM, there are two things. You need to move the VM, so you move the memory from one node to another, and you have the related data to that VM. I know in VMware, I'm sorry, I don't know in Xen, so you do vMotion. And you do storage vMotion if you want to.
Yeah, it exists too.
Okay. So the idea here is to create a central data repository managed by the DPU itself, which provides the same quality of service of access to whomever host connected to that fabric. So you don't need to move the VM anymore. You don't need to move the storage anymore.
So from Citrix point of view, we are getting requests from partners to support NVMe over Fabrics, and we are currently working with one of them on supporting VV over Fabrics specifically over fiber channel, because it's easier for us to start with this because we already have support enabled for it in the current version of the .0 kernel that we ship. But as far as I understand, here we need NVMe over Ethernet or over TCP or whatever, right?
So yes and no. That card here is seen as an NVMe device. So I just explained that the card takes control of the internal drives and show them as NVMe device resources to the guest VMs. Now, if you look on the right-hand side here, let's say this is an NVMe OF array, right? TCP or Rocky. If I connect that array directly to the host, then you're right, I need NVMe OF support. However, if I connect those LUNs through the cards, those LUNs are seen as drives, right? So for us, we don't care to have local drives or remote drives. It's just a drive.
It's only a local drive anyway from the DOM0 perspective. So
and then yes, it's going to be seen here as a local resource. So you don't need any NVMe OF driver at all.
So it's just to be smart enough to manage the knowledge that we are using this behind to pass the right PCIe addresses and to move them and reconnect on destination where it's needed, etc. So it's basically writing some logic, but other than this, that should be enough in theory. Obviously, maybe we'll find some speed bumps or things like that. But anyway, I think that sounds to be the easiest way to achieve it. And well, at least that's why next week we will start to make a POC. But that might be very interesting. I mean, writing a driver telling that this local drive is in fact shared because it is, I think it's just a matter of logic. So that might be enough.
Yes, sorry, go ahead. You go.
So the problem here, yes, that we need to have the storage shared, and we need it to be shared in the way that the access is synchronized between different hosts. And what we do currently, we have a clustered storage, right? So the Xen server and XCP-ng provide the GFS2 like layers, and in this layer you can use the a simple LAN like somewhere in the Xen, and you can use it synchronously between various hosts by formatting it in GFS2 and then storing your virtual disks in this file system. And so this is one way to deal with it. If this clustered logic is somehow embedded in this magic card or whatever you have, then we don't have to deal with it, right? There is different levels.
Correct. That's correct. You don't have to deal with that. You don't have to deal with integrity and all of this. You just have to release the resource on the first host before connecting on the second one when you live migrate, but the data will be exactly the same. So in theory, you don't even have to deal with all the cluster thing. That is, I think, the goal of a DPU is to offload all those difficult questions to the card itself, all the logic to the card. The only logic you will have in theory to manage is the link between the NVMe virtual function and the guest, which guest is connecting to which guest disk, in fact, is connected to which NVMe address. That's all you need to know. And a question, Jean-François, do we have the exact same address on the, for example, on the whole cluster? That might be easier to
That's a good point.
Yeah,
I don't know because it's early days, and I don't know if the device will be the same on host 1 or 210, but whatever number we have, I don't know.
But that would be logical to have the same naming convention on the same cluster, so you know that if you are using the disk2 is using the VF number 2, for example, then it will be the same on all hosts, and you don't have to do any complicated computation and to see or maintain a database to know that. That would be perfect. I mean, even easier.
So what is the thing is, if you have a drive, an internal drive, the NVMe emulation will be one ID, but the NVMe OF is not an NVMe ID. It's an NVMe OF. It's a NQN. So the ID you're going to get for that drive internally and externally is different.
Yeah, sure. Because you can have one big volume, one big LUN that will have multiple disks inside. For example, if you use LVM or something like that. But the only thing that matters to me that the guarantee that the VF I have on host 1 will have the same replicated data on host 2, regardless what's going on inside.
And I suspect it's not going to be the same VF. So
okay, so we'll probably have to maintain at some point a kind of a key map with which
certainly yes.
Yeah. Okay.
Yeah.
Well, that's not a big deal. It's just metadata in the end. So.
Yeah, and for us, the approach we want to have is to be wide open, so that the only dependency between any OS here and the DPU is NVMe, which is a standard, right? If we start to make something very proprietary, it's going to be like a nightmare to maintain for the different OSs, and it's not the spirit of having SPDK, right? NVMe and support the standard. We want to have it as much as we can open to support all other virtualization OS and environment, right? So this is key, right?
Yeah. And another thing what about the usual snapshot mechanism that's very
Mm-hmm.
really handy in the virtualization world when you want to have to go back in time, or even being able to export the content of the snapshots to make a backup.
So as of today, if you look at SPDK, right? Once you and we are working on that logical volumes. So as you say, you're creating a lambda size you want for your VM. The beauty of SPDK, you have a lot of features, and snapshot. As soon as we have logical volumes, we have snapshot and clones included. Okay. So that feature. So for us, we are planning to get that by the end of the year. So you get logical volumes, snapshot, and clones. And again, this is a new drive. You're going to expose as a VF, and you're going to get a snapshot. But the beauty of that snapshot, you can have access to that snapshot to the local guest, to the local host, but you can promote it over NVMe OF. Let's say you want to run your backup, and you don't want to load your main host during the backup, right? You take a snap. Okay, it creates so you need to coordinate the snap activity with the OS so that the snap is consistent, right? I think this is the first thing, is how do I take a consistent snap? So you orchestrate that, you create your consistent snapshots. And one interesting thing is, okay, I'm going to promote that snapshot across the wire to a backup node. So the backup stream will not affect the host at all, because the data will be managed by the card, from the drive to the card, to the kernel, to the Ethernet, not charging, no NIC, no OS involved here, goes straight to the backup host. So you can have a completely offloaded backup mechanism, which could be really interesting.
Okay, another question regarding going back to the live migration. So let's imagine that we detach we move the guests from one host to another. So we will detach the initial disk on the original host, and you will attach the PCI device, virtual PCI device, on the destination, on the guest that's moved. Do we know to reinitialize the device? Or I mean, how the guest will see the device? Would it be the exact same device from the guest perspective, or will it be different, or do we need to initialize anything from the guest perspective?
I anticipate it's going to be different, because let's say this guest here mounts virtual function 1. If you move that VM to another node, then the data, without moving the data, that device here will be seen across NVMe OF to another card and another virtual function. And I'm guessing that virtual function will not be guaranteed to be the same as this one. So there will be a mapping thing to be done so that it's smooth.
Okay, so maybe we have to do indeed some mapping in the middle to be sure the device will be seen as exactly the same at some point.
Yes. Okay.
And maybe initialize the device or something. I don't know. That might be interesting to investigate on that.
It's really the aim, right? Is to allow transparent live migration with a minimal impact and without any data transfer.
Yeah.
And obviously, yes, mapping will be involved. Yeah. But it's my guess based on my experience. I'm sure we will have to experience it.
We got a remark from George about, as he said, more creative solution where we could maybe no dump zero at some point, or having a way to control things directly from the card. I think that's what VMware wanted to achieve with the project Monterey, where they're running the E6i directly inside the card, and you might have some environments without even running the virtualization platform on top of it, the x86 one, but you can manage things directly from the card. But if you do that, that would require, I suppose, at some point to run, I don't know, could be something else into the card, depending on what do we want to achieve. So I suppose you ported a very, like you say, lightweight Linux inside it.
So yes, so what you have to have in mind, our way to design, this is a homemade GPU. This is not an ARM, this is not an AMD, this is a homemade core, right? We have designed it. It took us like 11 years to design that core. This is a third generation core, right? So, and this core along with coprocessor is really to manage data. So we have ported I don't remember which version of that embedded Linux. So it's not a full Linux. So for instance, we had a discussion with a partner who has a very nice management platform, but the satellite is a satellite which is really at the edge, is running in a Java runtime. And unfortunately, Java runtime cannot run on the card, or it's going to be a long process to port that Java runtime and all the libraries on our core, right? So this is today what we have. And the discussion we may have with our software architects, hey, okay, having that running on the Linux will request those libraries. Is that possible? Not possible. It's very difficult if you don't have the list. But we have to anticipate something which may be a bit difficult if the software is too big. We have enough power, right? We have 16 cores.
But it's just a matter of adapting the software to the hardware, which could be really hard. Yeah,
exactly. Yes. So again, this would be the discussion we will have, and what we can do, and how long it takes. Our goal is just something as fast as possible to market, and then see what enhancement we can do.
Okay, so to me it's pretty clear. I don't know if there's other questions regarding this. We will obviously keep everyone on track. We'll have some real field tests. As I said in my presentation, Carrie is based in Grenoble, so I will come to a workshop with them with the card, so I will be able to test it in real condition. And as I said again, we'll try it with a very simple test scenario where we will directly pass through local NVMe drive through the call record exposed in virtual NVMe VF to the guest and see how it behaves and if it's working correctly. So yeah, George.
Indeed. Agree.
Well, I would say baby steps. So let's see if we could already have something work correctly. If I have any question to you, the Xen community, I will not hesitate to ask about maybe some specifics on the PCI pass-through. But I have a feeling that it might work pretty well, and then we will continue to dig on the integration itself to write some logic. In Xen server or XCPNG, you have indeed the storage stack called SMAP, and the V3 is able to deal with that kind of thing. So
there's a question from
George. Yeah.
Yes, why not using a generic ARM and RISC-V core? Because when we started the project, RISC-V did not exist. So it's a project from a well-known lab in France. And the goal of that project was to design a massively parallel processor, for the embedded world first. We have two entities in our company. One is for embedded systems, and we are designing cards and systems for autonomous driving projects. And in that constrained environment, you need to have a very low power environment. The other thing we have thought about is that processor is integrating neural network inference algorithm, hard-coded, right? So all that together need to be low power, and ARM is definitely not good power enough, and RISC-V was not mature enough to get started, right? Obviously, we ask the question from time to time, for next generation's processor, shall we have control plane managed by a RISC-V core? That's a very good question. So for us, it's a third generation processor. And we continue our project, because this is for us a key moment, because this is the first time we will have a processor in mass production. So this running those days, but we are considering those modification, but we're not sure it's going to be efficient enough for us. But obviously, it opened the door to many things, and there are several ways to do it from now. So this is the second project we are driving with VATES. We are also developing a storage appliance or flash array, and obviously we don't need ARM at that level. So integrating the host will open door. We'll see that in the future. I hope it answers your question, George. Thank you. Good point anyway. We'll make sure you provide you answers as we go.
Okay, great.
I think we are done.
Thanks. Yeah, thanks, Jean-François, for being here. Another question, the last one from George.
You're not expecting anyone to upload their own functionality? Yes, because we are SPDK based, and we have tried that. One customer talked to us, hey, we see that we saw that feature in SPDK. It's running on my x86. I would love to have it on your card. And it took our developer to compile it in one day. So within less than 1 week, we had a draft. So you can go ahead and in less than 3 months to have a full product. So yes, any SPDK module developed on the top of SPDK will work on our card. So yeah, it's going to be open. So today it's not yet. We don't have the SDK from our perspective, but happy to consider those ideas. Let's say you have developed a nice storage feature on the top of SPDK running on your x86, provide it to us, and we will port it on our card if it makes sense and provide features. But we can do that. Yes, it's open. Not yet open to upload, but will be as an SDK feature in the future. You're welcome. I think we're done.
Yes, time's up. Thanks, everyone.
Thank you very much, guys. Bye-bye. Have a nice weekend.